Okay, so the contest is over. We solved, I mean, we solved all four problems. So let's go through them. So it's taking time. Okay, so first problem. Uh, so in this we are given an integer n, and we have to return true or false if according to if the the binary representation of n contains exactly one pair of consecutive bits. That means like something something one one something, like mostly zero only, something like that. But it can have like one here as well, here as well. That's fine as long as this is only one pair. So the way I have done it is I declared a variable for found. So found is for like if I have found the pair, so it is false. So the thing is that if let's say something something the pair was at the end over here, that means if we just choose these two bits, they should be equal to 3. So that's what I've done. If n ampersand 3 equal to 3, that means the last two bits are set. That means we have found a pair. So if we have already found a pair before, we return false because we have multiple pairs and we have to tell exactly one. Otherwise, we set found as true, and then we shift n by one bit. So this will handle like if we have case like 1 1 1. This is also bad because we have two pairs. So we'll only remove one bit so that these two can be done checked later on. So in this I got a penalty because I thought that we only need one pair and all of them should be zero. So I got a wrong answer on with this solution. Like I just check if only one, like only one is there and rest all are zeros. I thought something like that will happen, and that is not the case. Okay, problem 2. Okay, so here we are given a brightness, the number of bulbs, and some time interval. So we have to tell for each time in the time interval, we have to make at least uh, brightness equal B bulbs illuminate. And it is given such that like if we just turn on a bulb, then this its adjacent ones will also illuminate. So this is the scenario. And we have to tell the minimum number of bulbs we have to turn on across entire time. So the first observation is that we like since brightness is less than n, we need not worry about edge cases much. If we turn on one bulb, it can illuminate up to 3 bulbs. So the number of bulbs we have to turn on is brightness divided by 3 seal. So this is what I've written here. The number of bulbs should be brightness plus 2 by 3. This is like the seal function, seal division. And then for over like in intervals there are some intersections, like in this case 1 3 and 2 4. So we have to take care of this overlap. Like this was the basically the main problem only, like merging intervals. Like this is a standard problem, merging overlap intervals. So that is what we have to do. Then for each time period in the interval, uh, these many bulbs will remain on. So we will just take some of them over the time period. And this is like a standard idea to merge intervals, overlapping intervals. Yeah, so that's second problem. Third one. Okay, so here we are given a binary string and an array. And for all those places that are 1 in the binary string, we will take the consecutive value in nums, take their sum. And we have to maximize this sum with the allowed operation that we can shift a bit left at most once. So like if I have this 0 1 0 1, either I can left this bit here or I can shift it here. So this becomes 1 0 0 1. Also I can shift this here as well. So this become 1 0 1 0 or accordingly. So like in this case, it will be better to have 1 0 1 0 here. And so the observation here will be like if we have some 0 and 1 1 1 1, so we can among these values, and let's say 0 here, so in these values we can just ignore any value we want and choose all the other values. So let's say this was 5 6 2 uh, 3 4 7 7, let's say. So in this we should we want to ignore this 2 because this is the smallest value. We want to find a maximum sum, so we will move this here and move this here. So this will become 1 1 0 and so on, like this. So and this will be like the configuration we have to set. So that is what I've done here. So I ran a 2 pointers. So in this range L to R, I'll have all the ones which are just after a 0, and then including the 0 to all the ones, I find the index with the smallest value. That index will be the 0, and we others will be 1. But if we have something like 0 0 1, we cannot set this at all. It is not possible according to the operation given. Then according to the ones, we find the sum at the end. So yeah, that is problem 3. Problem 4. Okay, this was a nice one. So maximum score with co-prime element. So here we are given an array and we are allowed the operation uh, with the limit of max value that we can choose any number in the array and convert it to any other number less than equal to max value. And there's a cost of that with the cost of 1. Then we have to, after this operation, as many times as you want, we choose an index I such that nums of I is co-prime with all the other numbers in the array. Then we have to tell the nums of I minus the number of modifications we have done. We have to maximize the score. So the way I have done it is I created an array non-coprime. So this will basically, for non-coprime of I, this will give me the frequency of all the elements which are like obviously like not co-prime to I or something like that. So like co-prime is that GCD should be 1. So in case of, let's say in case of 3 4 6, non-coprime, let's say non-coprime, prime of 6 will be 3 because that includes 3 as well, 4 as well as 6 as well. None of them have GCD of 1 with 6. And similarly, non-coprime of 4 will be 2. It will contain 4 and 6. It will not contain 3 here because 3 is coprime to 4. So how I've calculated this, I'll come at it later. But let's look this idea that after we have calculated this, then what have we done? We choose each value, like the nums of I, we choose each possible value of nums of I and check the modification cost for it. So the values will be all the values from 1 to max val and all the numbers present in the array. Because let's say in array we have 6, but a max value is 5. So we can still do the operation on 6. We can choose this as 6 without updating it, for example. So that's what I've done here. So it is like a union of 1 to max val and nums. Then for each I do this like this is the condition handling that. Then modify these value, like I find a number of values I have to modify. So the thing is that all the values that are non-coprime to I have to modify them. So let's say I'm choosing 4 as the answer. This is going to be my answer here, like the selected value here. So we have to update this 6. So and 3 is fine. We have to update this 6. We can update it to 1 only. So this will be co-prime to 4. So we don't have to worry about what if we will update it to. So this is fine. So here the logic to find a number of modified element is, first we have to find non-coprime of I. So for 4 it will be 2. So this will include 4 and 6. But 4 we are not going to update. So 4 we will remove from the answer. So if exist of I, so exist is like if that element is inside the array. Since we can go to 1 to max while we are iterating over each value, so we'll see if it exists in the array or not. If it exists, we will decrease modify by 1 because we don't have to update 4. Otherwise, if I does not exist, then we need some value to become I. So that is the trick here. Like if modify is also 0, there are no numbers co-prime to I, but still we need one operation to make uh, the value one value equal to I. So let's say if I was choosing I as 2 here, let's say not 2. Let's assume it's 12. Ideally not a good example, but or let's choose it as 5 only. So for 5, we want I is going to be 5, this I like the selected value. So number of non-coprimes of 5 is 0 because all are coprime to it. So modify is going to be 0, but we need to have modify as 1 because we need 5 in this. We don't have 5 right now. So if modify is 0, like 5 doesn't exist in this array, so we have to, and modify is 0, so there's no coprime number coprime to 5, so we have to modify that as well. The reason for this condition is basically let's say I choose 2 here. So non-coprime of 2 is going to be 2 including 4 and 6. In this case I will not set modify as 1 because I will turn one of these values to 2 and others as 1. So I will kind of reuse this modification to get my I value. So that is the idea why I have done it this way, like the logic to find a number of modifications for this selected value I. Then I choose I minus modify as the current answer and choose the maximum over all ranges. There's one edge case here, like in my implementation for 1. So if 1 already exists and we choose that as a selected value, then we need not do any modification. So if 1 exists, I choose 1. Basically, this is 1 minus 0. If 1 does not exist, then we can do one operation to get a 1. So 1 minus 1 operation. So we will get 0. So this was one edge case. I've handled it this way because like co-prime, like I'll get to the implementation of this, then we'll understand why I've done it this way. So to find the non-coprime of I, how I have done it. So like let's say for 6 we want all 3 4 6 values, right? So what I've done it is this, let's say I choose some value uh, let's say I choose some value x equal to 2. Okay, so x is going to be a factor. Like if GCD is not 1, for non-coprime we are finding numbers that don't have GCD as 1, like that are not coprime to I. So their GCD is not 1, so they must have some factor. Let the factor be 2. So I'll find the frequency of all the even numbers, like the count of all the even numbers, and then I'll add this frequency to all the even numbers. Basically, like all the even numbers are going to contribute to each and every even number, right? So let me just write it this way: 0 1 2 3 4 5 6 6. Okay, so let's say for this example I start with x equal to 2. So I go 2 4 6. The frequency is going to be 2 because we have a 4 and a 6. So this will contribute to all the values. So this will, all of them will be increased by 2, right? Then we choose x equal to 3. and then we go to 3 to 6, so frequency is going to be 1 because 6 is present. So I add 1 in this and I add 1 in this. So here and then let's here you can see that this 3 has a 4 and a 6 and a 6. So the 6 is double counted here. So when we choose x equal to 6 later on, so we will only get 6 here. So the frequency is going to be 1. We are going to subtract 1 from it. So we are going to subtract this frequency because this contains two factors. So this is like the concept of inclusion exclusion. So here it has only one prime factor. Here it has one prime factor. Here it has two prime factors. So depending on this parity, even odd number of prime factors, we add or subtract the frequency to get our array. There's one minor thing more to cover, but let me cover this example, this wrong summation implementation. So here first we have found exist array with, like if it exists in the array already, and frequency. So now for non-coprime, for all the values, I start iterating from true because considering one is very tricky in this case, as I mentioned before. So now this f is going to be the frequency. So for I equal to 2, this will be the number of even numbers in the array and all. So I iterate j from I to the maximum value I've taken here, maximum chosen value, or to step by I. So this will contain I, 2i, 3i, and so on, all the multiples of I. So I take the frequency sum. So for x equal to 2, this will like the frequency of all the even numbers. Then I found a prime factors parity as I explained here. So this is like the parity 0 and 1 according to even odd. Then according to the parity, then I again iterate over all multiples of I, and depending on the parity, I add or subtract the frequency. Now this gave me a wrong answer because when x is equal to 4, then we are going to iterate over 4 and we don't go beyond that. The frequency is going to be 1 here for 4 as well. But if we increase this, then we will have 4, 6 and 4 because this 4 was covered by 2, this is covered by 4. So this is a double counting which we have avoided in the intended solution. Yeah. So we find what is called a Mobius function. So Mobius function basically is 0 if we have the any prime factor appearing twice. So let me show this. So mu of n Mobius function is 0 if n has any prime factor appearing twice basically. So like any factor is a square, and otherwise it is minus 1 power k for each prime, like for k prime factors. So this is like the idea. So for mu of 6 will be 1, mu of 2 will be minus 1, and in this case our mu of 4 is going to be 0. So this was the final piece to this problem. So according to the Mobius, we choose it will be minus 1, 0 or 1. So according to that, we add, subtract or ignore the frequency here. One thing to note that we cannot just ignore the composite values. Like I first thought that just ignore only consider the prime values, but that is not true because like we consider 6 as well, right? So this is like, I'm not sure the intended solution, but this is the idea here. So yeah, that is how I solved the fourth problem. I hope that makes sense. So that's it from my side. Thanks for watching. Bye.